every lecture that we had, and you give your ideas what you think if there's any force that could come from this section. So if you think back to fluid properties, is there any force that could be relevant in centrifugal microfluidics?
Viscous?
Sorry?
Viscous force?
Viscous forces, yeah, so that's rather, viscous forces rather in the fluid dynamics area, because then you are talking about motion, fluid motion. If you think about, okay, would this viscous force be intrinsic or extrinsic?
Intrinsic?
Right, yeah, so that you always have it, you can't really do anything against it.
Gravitational force?
Sorry?
Gravitational force?
Gravitational force, right. With the context that I just mentioned at the start, that the centrifugal force is way stronger than the gravitational force. In most of the cases you don't have to consider it, but there are cases where it can get important. So if you think about gas, do you have any idea for fluid properties? So I think at the start we were talking, in the first lecture we presented an example where you compressed air and decompressed it again. And this is something that you can also use in centrifugal microfluidics. So you can compress air, store basically the energy inside the air, and when then changing the rotational frequency, this air will decompress and it can transport liquids. I will go into detail later on, but usually we call it pneumatic forces, which come from this air compression effect. Okay. So, and one of your colleagues online said viscous and capillary, so the viscous forces we already had, and the capillary forces, obviously they are part of this surface effects lecture, and so that are our three intrinsic forces that exist in centrifugal microfluidics. So you already can see that I also highlighted electrokinetic effects. They are obviously not intrinsic, right? So they come from, you have to apply some kind of electric force field to get the liquid moving. Is there any other extrinsic force that you could think of? So especially, I mean, you've probably had it in your studies. If you think about electrokinetics, there's always a second force that comes along depending on how you apply the electric. Magnetic forces, right. So that's also a potential that you can make use of. So you have external magnets, you have magnets in your liquid, and a very simple example would be that you have little magnetic particles in your chamber, and you have an external magnet, and you just use this interaction to mix your liquids. And the last thing that we haven't really that is a potential that you can make use of, but which is not used very often, nevertheless it exists, that you use externally actuated pneumatic forces. So this goes more into the direction of pump-driven microfluidics, but there are research groups out there that combine both worlds and make use of pneumatic forces as well. So, and now we will quickly go through the different forces, what the parameters are that are of importance for them. I think many of these forces you will be familiar to or with, and as we usually work with pressures, because it makes the calculation simpler, I depicted all the forces as pressures in this next slides. So on the right hand side you can see the setup, our cartridge, the position of the liquid column and so on. And the first thing that you can see if you look at the centrifugal pressure is that there is a dependence on the liquid column height. And this is something that you might also know from the gravity as well. So if you think about the sea level, the deeper you go underwater, the stronger the pressure on you will be. And in case of the sea level, if you work with the gravity field, it's a linear dependence. So you have a linear rise which scales with the gravity force. In our case, in the centrifugal microfluidic world, it's to the power 2. So the bigger the distance here, the stronger your centrifugal pressure will be. Once again, the Euler pressure, it depends on the acceleration rate of the frequency, but it also depends if you have a pressure on the isoradial length of your liquid. So this is, if you think about it in a very simple way, if you have a liquid column like this, and a liquid column like this, in this case, the Euler force would be larger than in this case, simply because you have a longer isoradial distance compared to this one. Yeah, and then once again you have the viscous pressures. So here, Niklas and I mention it quite often. Here it's important to understand what this resistance, hydraulic resistance is. And what's your estimation? What would this resistance look like? Do you have any ideas? So what would you expect? What would the flow profile look like in a channel? So let's assume we have a radial channel. That's our velocity. What would you expect the velocity to be at the wall? 0, right? Because the wall is fixed and the velocity will be 0. So how would the profile probably look like? Yeah, right. So it's once again you assume that the flow profile is described by Hagen-Poiseuille, the Hagen-Poiseuille law, and that's where you also get your resistances from. So you have, that's what we what Niklas presented last time, and I think also in the calculation lecture and simulation modulation modeling lecture. And the resistance value, you will get it once again from this idea that there's a Hagen-Poiseuille flow profile within the channels. So the viscosity will play a role, the dimensions of your channel will play a role, the length of your channel will play a role. So yeah, you should be familiar to this and by just looking at the last lectures. So then you have the inertial pressure, which comes from the change in the flow rate. And you have capillary pressure, which comes from your dimensions of the channel and obviously the interaction between liquid and solid. So it's based once again on the surface tension and the contact angle, because you have a three-phase system consisting of the cartridge material, the liquid, and the air. And finally, that's what I mentioned before, the pneumatic pressure. So the idea of this pneumatic pressure is, on the left-hand side, you can see that it's based on an ideal gas. So this is nothing else than the ideal gas law that you learned in the first lecture with Niklas. And it's also depending on the vapor pressure. So if you think about it, if you have a small liquid volume, you heat it up, let's say it's water, you heat up to 100 degrees, you have evaporation, and obviously evaporation generates a pressure that can become very important in microfluidic settings. Yeah, and so what is depicted on the right hand side here is the principle of this pneumatic pressure generation. So if you have a closed volume of let's say V0, and you now transport this liquid column in this direction, the volume gets compressed, and that's why by the ideal gas law the pressure rises until you reach a balance between, in this case, the centrifugal pressure from the liquid column and the ideal gas pressure, so the pneumatic pressure. Okay, so that's it for the basic forces that are of importance. And we will now move on to the different unit operations that exist for the centrifugal microfluidic platform. So you can see that there are lots of them, and I hope that you now understand why we only covered a few of them in our unit operation lecture, because there are many concepts and we just want to teach you how you can understand unit operations and how you can get to understand them yourself, so that you don't need to ask other people all the time. And so this lecture I focused on a few important ones, which are one of the main advantages of the centrifugal microfluidic platform, and which lead to this idea that the complete platform is very simple and easy to use. And to start with, I will present the stick packs as solutions. So the stick packs, that's what we call these little aluminum pouches here. And in these pouches you can store liquid. So they are closed on both sides, and inside there's liquid. That's what you can see on the right hand side. So you have a tube that injects liquid into these pouches, and then they get thermally sealed, so they are pressed together and with heat to close them. So what's your guess? How can we get the liquid out of those pouches? Do you have any idea?
Maybe the weld breaks up to the pressure inside.
Mm-hmm. Right, yeah, so they break up because of the pressure inside. So if this is our stick pack, I'll just make a cut. So it's tightly sealed here, it's tightly sealed here, and then you have liquid inside. And this liquid will lead to a pressure because of, if you now start rotating, because of the height of the liquid column. And this pressure will peel open slowly this closed area down here, and at one state it's completely open and the liquid can move out of the system. So that's one of the advantages. You just put it on your cartridge. You don't have to open it manually. You just have to start rotating, and the liquid comes out of your stick pack. So maybe as a concept, you often, if you get French fries in a restaurant, you often get this ketchup or mayonnaise packages, and that's the same principle. So if you use them and you really pressure it, you can get the ketchup out without really tearing them open. And the idea in this storage method is the same. Okay, then obviously liquid transport is also important here. And you can already see on the top that there are different ways of transporting liquid. The most important one is already a part of the name of this lecture, so the centrifugal force. Keep in mind, and that's really important, that it is linear to the power of 2 or proportional to the power of 2 of the rotational frequency. So At low frequencies, you probably don't have a relevant force, but if you go really high, it really increases quickly, and the order of magnitude of the centrifugal force increases dramatically. So in principle, you just add a liquid, you then start rotating, and the liquid gets spinned out in a radial outward direction. For this transport, you have to consider your channel dimensions, because once again, you have the resistance coming from the drag forces. The radial position is important as well, as we have seen in the pressure derivation. So the further outward, the stronger your forces are, the bigger or the larger the liquid column, the stronger the forces. And obviously, it's also important how your chamber is designed on the top, because by using different chamber geometries, you are able to influence the pressure as well. And maybe if you just look at two chambers and you tell me which one has a stronger pressure. So let's say we have one chamber that looks like this, very simple. We have one chamber that looks like this, and we have a third one which looks like this. So let's assume that the depth of all chambers is equal, and that we now add the same volume of liquid into each chamber. So what's your guess? Which chamber has the highest and which chamber has the lowest pressure?
Number 1 is highest and 2 is lowest.
Yeah, so I agree, number 1 is definitely highest. 2 is probably the lowest, and it's simply because this area here would be probably or resembles to the, because the depth is equal, we just can have a closer look at the areas to have the same volume. So if we have the same area here, here, and here, approximately, then you can already see that the liquid column is much larger here, so you have a larger distance in radial direction. And that automatically means, if you think back to the pressure equation, that you will have a higher pressure originating from this liquid column than from this liquid column. So for this chamber here, it's a little hard to evaluate because it's not that easy to fit the same area or to have exactly the same area, but I just wanted to make a statement with it that you can also think about think about other structures. So by making a smart design, you can influence your pressure and control the flow rates that occur in your microfluidic system. Okay, so the second liquid transport principle is based on kinematic forces. And so what you can see here is an inlet chamber where you have some liquid inside. You have a target chamber where you want the liquid to be. And there are some other structures that you require to transport the liquid. So this is really a good example of the main challenges of the centrifugal platform, because your driving force goes always in outward direction. So if you want to move the liquid from here to here by centrifugal force, this is simply not possible, because there is no force in radial inward direction. And that's why we were required to develop alternative solutions. And one solution was developed by Steffen Zehnle here in our lab. And he developed a solution where he makes use of pneumatic forces. So he makes use of this fact that you can compress air and decompress it later. So the idea here is that you start rotating and the liquid gets distributed within your structures. So the chamber down here is closed, that the air can't leave the chamber. And when the liquid moves into this chamber, it compresses the air and you have a pressure that builds up within this chamber. It's very important at this point that you have a look at the height of the liquid column. So for these two channels, it's at this position, and here in the chamber, it's at this position. What's your guess? Why is that? What would happen if those two were at the same position here? Okay. So the system that you're seeing is in equilibrium. I could continue rotating, nothing would change. And that's the important thought at this point. So, a little bit simplified. So you have a pressure in here. So if it would be at the same position here, there would be no pressure difference between the fill levels here. And obviously the pressure here and here is atmospheric pressure, because we don't have any pressure buildup in these chambers. And in this case, the pressure from the gas would push your liquid in this direction. And if you now go back to the slides, what you can see is that the height inside the channels is further radially inward, and that automatically means that there is a centrifugal pressure applied onto this chamber. And what we can see in this slide is basically that there's an equilibrium of centrifugal forces and kinetic forces. So, if we now reduce the rotational frequency, what would happen?
Yes, volume would expand and push the fluid.
Right. So the air will expand, and at the same time the centrifugal pressure would get lower because we reduce the rotational frequency. And now it comes into play that you can make use of hydraulic resistances. So in this design, this channel here has a very high hydraulic resistance by being very small, for example. So having very tiny dimensions for the width and the height. And the other channel has a high resistance. So if you now apply the same pressure on both channels, the flow rate will be much higher in direction of the low hydraulic resistance. And that's what we make use of. So you reduce the rotational frequency, there will be a flow in both directions. So there will be a flow in this direction, there will be a flow in this direction along both channels. But because of the high resistance, the flow back to the inlet chamber will be much lower than it will be in direction of the target chamber. So what Steffen Zehnle has demonstrated was that you can achieve a transfer efficiency by making use of this principle of 91%, by only working with pneumatic and centrifugal forces. If you think about the ideal gas law, how could you increase the pressure in here? that's the volume is kind of fixed in this case because it's defined by the chamber. But if you think about, let's go back to the ideal gas law, there are other parameters that you can make use of. So the volume is fixed because it's defined by our geometry, but you still have the amount of substance you have and the temperature. So in theory, and what we often do in our daily routine is that we use temperature because we need it anyhow for our biological assay integration. And by increasing the temperature, you can increase the pressure even further and get much better efficiencies for the transfer. Okay, so the same principle can be used for welding. So the main difference is here that in the case that I just, in the liquid transport case, you use the pneumatic pressure to transport the liquid. In this case, you only use the pneumatic pressure to get the liquid over the siphon, and then when you have passed the siphon, you have a centrifugal force that transports the liquid outwards. So if I go back, at this point, if the design is like this, you wouldn't get the liquid into the radial outward chamber because it would have to move first radially inward and then outward. And by making use of this pneumatic pressure, you can, by quickly reducing the frequency, prime the siphon and move a part of the liquid over the siphon. And as soon as it moved over the siphon and is going down into this chamber, you have a radial or a liquid column from here to here, which allows to transfer your liquid by centrifugal forces. Okay, so now let's come back to the Euler forces. What you can see here now is a mixing unit operation. So you have one liquid in a mixing chamber and you add another liquid by centrifugal force again. And now you want to mix those two reactions. And you can do that by making use of the Euler force. So the idea is that you quickly move the disk back and forth, and thereby you add forces in isoradial direction, the Euler forces. And this will swirl your liquids and mix them. So I think, yeah. So that's only based on the Euler force. And finally, it's only important how fast you can accelerate and decelerate your rotational frequency. Yeah, on the right-hand side, you can see a simulation that we made to illustrate this. And it's very typical, those swirls that you see, they are very typical for this shake mode mixing procedure. In the end, what you do is you increase the contact area between both liquids. And by increasing the contact area, you also simplify the diffusion process. This is something that we have also seen quite often in our lecture. And the final unit operation I just presented because it will be part of the next example is fluorescent readout. So in principle, if you have a point of care testing, in the end you want to get some answer to a question. So does the person have COVID or does it not? Does he not or she? And what you then do is a PCR, for example, and in the end you make a readout, you have a look at your chambers and you check is there a positive or a negative signal, and then based on those signals you can make your decision. So there are other options on how you can do a readout. A millisecond readout is also possible, or you can also look at the color shift. In general, for those kinds of tests that we are developing, the fluorescent readout is the most prominent. Okay, and to finish this lecture, I want to give you a short introduction on the system that